Okay, so let's look at some of the mechanics of muscle contraction. And there are two different ways of looking at muscle contraction. So when you work on the PhysioX, you can measure the electrical current. All right, so we look at the electrical current activity, and we give a stimulus to a muscle cell. That is going to result, it's a sufficient stimulus to reach threshold, all right? So we're not going to see that graded potential necessarily. That stimulus is strong enough. But I'm going to go ahead and put it in there. And so it looks very similar to what we see in the neuron. Draw that a little bit bigger up down here. So this is the action potential of a muscle cell, and a skeletal muscle cell, and it's what's happening along the sarcolemma. All right, so it's measuring the change in electrical current along the sarcolemma. So we would have a resting membrane potential here, a graded potential, and that's going to be at the motor end plate due to the acetylcholine. All right, and if that graded potential is strong enough to reach threshold, then the voltage-gated channels of the sarcolemma open, and we create an action potential, just like we saw along the neuron. Okay. So as a result of this, the muscle cell contracts. Now, if we look at that, now we're just looking not at the action potential, but we're looking at a graph of the tension or the force created by the muscle contracting, the muscle cell contracting. So in this case, this would be time. And instead of current, this is going to be tension. And so we have the membrane cell is not, the muscle cell is not contracting. We give it a stimulus sufficient to reach threshold. The muscle cell contracts. And the muscle cell relaxes. Okay? Because we're measuring tension. So this would be, rather than depolarization, this would be contraction, and this would be a relaxation. It's probably not a point, it's probably more of a curve, but at any rate. Now, notice that there is a gap of time. If this x-axis is measuring time, there is a gap between the stimulus, if this is an electrical current or even the acetylcholine being released, and the muscle cell contraction. This gap is known as the latent period. Okay? So if we trigger, I decide I'm sending a neuron down, and I have a trigger, release the acetylcholine from the end of the synaptic gluton, and there's a latent period, a few microseconds, 2 or 3 microseconds before my muscle cell contracts. What are the events that would be taking place during that latent period? What has to happen for tension to be created? What's creating the tension? The myosin pulling on the actin. That's when we start to see a change in the tension. So everything that occurs prior to myosin binding to actin is going to be occurring during the latent period. So the acetylcholine binding to the ligand-gated channels, the graded potential moving to the voltage-gated channels, the action potential moving down into the cell, the calcium ions moving out of the sarcoplasmic reticulum, the calcium ions binding to the troponin separating from the tropomyosin, until the myosin actually binds to the actin filaments. All of that is latent period. Okay? Then the actin, the myosin pulling on the actin, hand over hand, if you will, creates the contraction. And then relaxation begins as soon as the level of calcium ions starts to drop. and troponin starts to move back to the actin filaments. Okay, so that's just kind of a review of those steps that we covered, and again, those are listed in the lecture notes.
So the latent period that we need before and after.
Well, the latent period is what happens between the stimulus and the first creation of tension. Okay? Now, if we're talking about the creation of that tension, there is some activity that occurs before that tension is created. Remember I talked about the titin? So if we have our myosin, must be purple. We have our myosin, and then we have the titin attaching that to the Z disc, and we have our actin on the Z disc, and the myosin head reaches up and pulls on the actin. There's going to be some slack in that spring-like titin first before the Z disc moves. Does that make sense? Okay, so if I'm pulling on the actin, but there's a spring-like activity here before that tension is generated to it, it's going to take a little bit of the energy to do that. Also, outside the muscle cell, remember we have the endomysium, and around the fascicles we have the perimysium. So that has to be stretched too before we actually start shortening. You have to pull on that and overcome that resistance. So it's kind of like if I'm pulling somebody across the floor, I have to pull a while before I overcome the peripheral resistance of them on the floor itself. And so some of that force that's being generated is going to overcome the resistance to the moving of the actin. Now when we measure this force, this is done with a contraption that looks a bit like this. Okay? This is a whole muscle, like the gastric meatus is often taken out of the back of a frog leg. And so when we look at muscle contraction, we need to be clear whether we're talking about a single muscle cell or a muscle, like the gastric meatus. And I'm referring to now to changes in contractile force that appear. So let's say, again, back to those of you that did Physio 8.0, and you were asked to stimulate a sciatic nerve. And you kept turning up the power, the voltage, and you got an action potential. All right? All or none says that if you were to increase the force of the current required for that, you should see the same strength of the action potential. Because we're not going to open those voltage-gated channels anymore, even with the stronger force. What did you actually see, those of you that did the 8.0 exercise? Anybody here that still did that? All right, so with the sciatic nerve, we talked about this a couple of weeks ago. As you increase the stimulus, the action potential increases. How do we explain that in light of the all or none response? Exactly. Terry's saying there are multiple neurons. Each neuron obeys the all or none rule. But each neuron is going to have a different threshold. So at this particular strength, we reach the threshold of a few neurons. Here we add additional neurons, and therefore action potential is higher because we have the electrical current of their action potential and so on. Okay? So we can use that same understanding when we talk about a muscle cell. Right? A muscle cell has an all or none rule as well. It's going to contract for a particular strength of a stimulus. But as we change the strength of that stimulus, we're going to increase the recruitment of additional muscle cells. So this is generally measured by taking a muscle, like the gastric meatus, and suspending a weight on it and stimulating it with an electrode with varying degrees of current. And then this is attached to an arm that makes tracings along a piece of graph paper. Now, we're measuring force when this muscle contracts, right? We're not measuring electrical current. Don't have the electrodes inside muscle cells. So single muscle cells can be isolated, but often it's the whole muscle that's contracting. So when we look at an image, with this, and now we're going to talk about a single myofiber. Okay, not a whole muscle like we have in this image. We're just checking the force of a single myofiber. So there's zero tension. Vertical line is measuring tension. All right. We give it a stimulus of an electrical current. Nothing happens for a single myofiber. What does that mean? We haven't reached the threshold level of the gated channels along the sarcolemma. So we haven't changed the status of the voltage-gated channels of the sarcoplasmic reticulum. Calcium doesn't move. The muscle stays relaxed. So we give it a stronger stimulus. All right? We're not looking at action potentials or graded potentials. We're talking about force. The muscle contracts, and the muscle relaxes. Okay? That's a muscle twitch. Now, if we were to give it a stronger, allow it to rest, give it an even stronger force, we wouldn't see any change. We would have the same force of contraction. Now let's look at a muscle bundle. The gastrocnemius. All right? We'll ignore the first one that doesn't work. We give it a stimulus. The muscle cell contracts. The whole muscle bundle contracts. We give it a stronger stimulus. The muscle contracts more. We give it a stronger stimulus. The muscle contracts even more. Similar to the change in action potential from a nerve versus a neuron, what's happening here is we're recruiting additional muscle cells. So we might have a couple of muscle cells contract, increase the current. We've reached the threshold potential of 10 more. That increases the force created by the muscle shortening. Okay? So we can explain that anomaly by the fact that we're recruiting additional muscle cells. All right. Simple enough. Now let's look at this situation. Back to a single myofiber. All right. We provide a stimulus. The muscle cell contracts, relaxes. We provide the same stimulus. Muscle cell contracts to the same degree, relaxes. We do it again. And now as the muscle cell is starting to relax, we stimulate it again. With the same force. Notice what happens. We get a greater contraction. This is a single muscle cell, so we're not recruiting additional muscle cells. Single myofiber. But yet, we're getting a greater force of contraction. Two things are thought to provide or explain this phenomenon. Remember I said a few minutes ago, when the sarcomere stretches, we've got that titin that's getting pulled and the external collagen fibers that we're overcoming. So we've already done that with this. Okay? We don't have to do it again. And that happens, that more explains this. If we do it really close together, it completely relaxes and we can still get a greater force. And that's usually explained by the external connective tissue. In this one, what would you say is the state of the internal aspect of the cell when it hasn't completely relaxed? What's going on inside the cell? What happens when the muscle cell starts to relax? Thinking about calcium ions. So calcium ions are being pumped back into the sarcoplasmic reticulum, and some of the troponin is moving back into its association with actin. So if we haven't completely relaxed, then we haven't completely pumped all the calcium ions back into place. There is a direct relationship for the amount of free calcium, or calcium bound to troponin, and the amount of available actin binding sites. So we still have calcium in the cytoplasm that hasn't been returned. Now we open up the voltage-gated channels again, and now we have more calcium ions than we had here. All right, so when the voltage-gated channels opened, let's say we have 10, 10 calcium ions in the cytoplasm, 10 binding sites for myosin pulling on the actin. The muscle cell starts to relax. Some of those calcium ions have moved back into the sarcoplasmic reticulum. So now we only have 7. But then we send another current, and we open up the voltage-gated channels again. And now we get 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. More calcium ions means more troponin has moved, means more binding sites are available, means more myosin heads are pulling, means a higher contractile force. Okay? So we haven't technically, theoretically, broken that all or none rule because we changed the rule. We changed the game. We have more calcium ions. Okay? So it's not quite the same situation. The environment is different. Hence, we have more contractile force. We have more heads pulling on the actin with more calcium available. All right, so if we keep doing this and not allowing relaxation, we go into techne. All right. And this is called incomplete techne, meaning there's partial relaxation. But each time, notice the stimulus is still the same value. So we just keep adding more calcium ions without completely returning the ones that were there to the cell. So more and more binding sites are available. And finally, if we have the stimulus close enough together, the muscle just goes into a spasm, either the muscle or the muscle cell, and we have a straight line, which is complete tetany. That's the maximum contractile force. And if we continue to apply that current, eventually the tension drops off. All right? The muscle cell is fatigued. It has no longer the capability of responding to the contractile force. So in the lecture notes, I talk about various types of fatigue. Sometimes it's just mental fatigue. You think you can't do it, all right? But you really, the muscles can contract, as can be seen by, somebody's totally exhausted and then there's an emergency. And they think they can't run another mile, but they do, all right? So that was really a mental fatigue. And then there's the fatigue that occurs between the neuron and the muscle cell. No more neurotransmitters, all right? The neuron has emptied its synaptic vesicles, and it can't stimulate the muscle cell anymore. Therefore, it's the nerve that's fatigued rather than the muscle cell that's fatigued. Okay? And then there's, more rarely, there's actually muscle cell fatigue, where the muscle cell has changed its pH, or it's, some of you may have done things where you're so exhausted that you can't move. When I started cross-country skiing, my late teens, and I was cross-country skiing Nordic, which is very narrow skis, no metal edges on my skis. You wax them, or you can buy them with what are called fish scales, or you can put on skins so you go uphill. But anyway, there's a particular skill in going downhill. I don't know how many of you have seen cross-country skiing. The skis are really long, all right, and they're narrow. And when you go downhill, you carve these gorgeous S's. And you go like this, and then you stand up and you turn and you go like this. You can imagine turning with these really long skis. And I was determined I was going to learn how to do this. And I tried and tried and tried, and I couldn't quite get it. The guy I was dating in Southern California would go into the mountains, and he wanted, he was like, let's learn to do the balance. He couldn't do it either. And so he would run, and then I would do a run, just going straight down the mountain. And he kept saying, drop your knee, drop your knee. And I finally hit a submerged log with my knee. I was like, I think it's low enough. So 5 years later, I got to Davis, and their outdoor school was taking a bunch of people up to the mountains to go cross-country skiing and go downhill. Okay, I'm going to do this. And we spent 4 or 5 hours carving these curved edges. And everybody else had metal edges to cut into the slope, and I didn't. And so every time I tried to turn, I fell. And I fell, and I fell, and I fell, and I fell. And by 2 o'clock, it was like, I told the instructor, if I fall one more time, I'm going to burst into tears. So I spent the last half hour with hot chocolate, and then we all went home. And I just bought a new bed. It was on the floor, and no frame. And the next morning when I woke up, I literally could not lift my head from the pillow. To get out of bed, I log rolled and fell onto the floor. And then I tucked my knees. I was on my abdomen, and I pulled my knees up under me and got up that way. I was so stiff, okay? And that's the closest I've gotten to actual muscle fatigue, where you mentally try to move something and you have none of the proper ATP, magnesium, calcium ions left in the muscle cell for it to work. That's more rare than the other types of fatigue. So you're more likely to have nerve fatigue or synaptic fatigue than actual muscle fatigue.
Learning how to glycogen and oxygen consider that, that's a common use of glycogen that almost certain things we know.
Say that again?
Learning how to oxygen and glycogen, like when you
Yeah.
have blood sugar and you just, you can still move, but you're exhausted.
Right. So we're talking about the sources of energy, and you can use up the creatinine, or you can use the anaerobic formation.
Yeah, those are the two most, if I were to say fatigue, can almost certainly be you're out of oxygen or.
But it shouldn't take. You should be able to recover
Yeah.
that more quickly than some of the contents that might take some protein synthesis to recover. And we'll look at some of the energy forms for that. Okay, before we get to the energy forms of muscle contraction, actually I think we're ready. Let's talk about the terms isotonic and isometric. You guys remember what iso means? The same, all right? So you've probably heard of the terms isotonic and isometric exercise. If iso means the same, then isotonic is maintaining the same tension but changing length. Isometric is maintaining the same length but changing tension. And there's a few more complicated forms depending on if you're contracting or relaxing while you're changing that form of tension. So let's say that this is a 20-pound dumbbell, all right? And I'm doing curls. So is that 20-pound dumbbell changing weight? No. So therefore, the same tension is required to move it. But the length of my muscle is changing. And so I'm shortening my muscle fibers as I move that weight. And then I'm shortening these fibers and maintaining tension so my arm just doesn't drop down like that. But that's the more complicated form that we're not going to get into. All right? So if I have the same weight and I shorten my muscle, then that is isotonic contraction. All right? What you see in this image here. So that's isotonic contraction. If, however, I increase the force without moving anything. So let's say I'm going to try to lift up this table. And I try, and it doesn't move. And I try harder by adding more myosin heads to the actin and it doesn't move. And I try even harder. What's happening to my tension?
Increasing.
It's increasing as I add additional myosin heads pulling on the actin. But my muscle cell itself hasn't shortened, so the desk isn't moving. Okay? So isometric is increasing force, but not length of the cell. So this is an isometric, pushing my hands against each other, is an isometric exercise. Okay? That can be dangerous for individuals with heart problems because it increases intrathoracic pressure and can make it more difficult for blood to be moved as pressure is increased around the heart. Okay? So the heart has to work harder. So someone's doing isometric exercises and they have circulatory issues, they need to be careful with that. Okay, this slide is also in the lecture notes. It's 3 sources of energy. Given in the amount of duration that is available to the cell. All right, so there's a molecule, most of you, well not most of you, some of you that maybe do bodybuilding or weightlifting have probably heard of creatine. All right, so creatine phosphate and ATP, creatine phosphate can be and creatine changing back and forth, can be a quick source. It can be stored in addition to ATP, and we can take the phosphate off the creatine and add it to ATP so that that's available to the muscle cell. So it's a sort of a additional quick storage form of energy. But it's not something that you can use to run 5 miles, okay? Because it's used up quickly. It's in the level of seconds that we have energy available to the cell. Some of you, I've never tried it, but you can buy it, okay? I had a student in the previous section that said he uses it, and he was asking about the timing, if you take it a half an hour before, and I have no idea. And I said, how does it, do you feel it work? He says, yeah, I have more energy when I go lift weights. I can, I feel stronger. I have more energy while I'm doing it. And the suggestion is after you've gone for a run or after you lifted weights that you should take a protein drink within 30 minutes, at least an hour afterwards. The muscle repair typically occurs when you're asleep, but when you exercise, the muscle cells get what are called micro tears. So maybe the amino acids are taken up by the muscle cell more quickly through those micro tears. I'm not sure, I haven't really studied into the physiology of that aspect of it. However, when a muscle gets stronger, a muscle cell gets stronger, or a muscle gets stronger, it doesn't do so because we make more muscles. It's similar to a fat cell. When you get fatter, you don't make more fat cells. You lose